Hi, everyone. Welcome. My name is Mike Rima. I am a senior cloud security engineer at Netflix. And at Netflix, one of my primary duties is to come up with security solutions to Netflix's extremely vast and rapidly growing AWS infrastructure. And talking to a number of AWS customers over the years, both large and small, there's a number of security use cases and challenges that seem to affect a wide range of customers. One of them is inventory collection. So for today's talk, we're going to discuss how we can inventory, track, and respond to AWS asset changes within seconds at scale. So for today's agenda, we're going to discuss why we're here, what exactly we're trying to solve. We're going to discuss some inventory collection approaches that you can take in your environment. We're going to talk about an open source tool that we currently own called SecurityMonkey, very popular tool. We're also going to talk about some challenges that we have faced with SecurityMonkey and some challenges that you might face if you were to build an inventory collection system yourself. We're also developing a new system called Historical that we're going to give a deep dive in. And lastly, we're going to discuss the desired AWS infrastructure state that we want to obtain at Netflix. So why are we all here? What exactly are we trying to solve? Knowing is half the battle. You need to have inventory and visibility in your vast AWS infrastructure. With this, you can answer a number of very serious questions. For example, which AWS resources do you have deployed in your environment? Where are they deployed? Are they configured securely? Did their configuration change? And who updated, created, or deleted a given asset in your environment? When did they do it, and how did they do it? Being able to answer these questions are important because it allows you to address a number of serious security use cases that you may have. Take, for example, if you're involved in digital forensics and incident response. If you are involved in DFIR and you're tracking an incident, you have to answer all of those questions. Have you been compromised? How do you know that? You want to detect if you have organizational policy violations, where you have applications that can access resources that they shouldn't be accessing. If that's the case, you want to fix that immediately. You also want to determine if you have publicly accessible resources. Sometimes it's OK to have a public S3 bucket. Other times it's not. You want to have inventory of which ones are public and which ones aren't. You also want to know if you have any tooling that is creating insecure by default configuration of resources. For example, do you have tools that are provisioning S3 buckets to be public by default? If so, you'll want to fix that immediately. You also want to determine the resource ownership of the assets in your infrastructure. Who created them? Why? Let's discuss some approaches to inventory collection that we can take. This is a security talk, and so there's a number of requirements that we have to meet. For security, we need to have timely and accurate inventory of our entire infrastructure. If it's not timely or accurate, it doesn't serve you any good. You also want to have a full view of everything. You want to look at every account, every region. You want a single pane of glass with everything at your fingertips. There's also the attribution aspect. We'll call this the CloudTrail context. CloudTrail is a feature of AWS that logs all API calls that are made against your environment. You absolutely need to have CloudTrail enabled if you want to have a good security story in AWS. It will give you the who, the what, the where, the when, and the how to the resources that you have. And you also want that change history. This is extremely important to know what changes were made, as well as when you're debugging an access control issue to see, did something change that broke something? So how can we collect inventory? Well, there's two main approaches. There's a polling approach, where you periodically ask AWS, what's the state of my infrastructure? And we're going to call this the are we there yet approach to inventory collection. And then there's an event-driven approach where AWS will actually tell you when your infrastructure changes. There are pros and cons to both approaches. To polling, the pros are that you can get a full and complete inventory of all of your resources on demand whenever you need it. So if you want to see all the security groups in a given account and region, you simply issue a describe security groups call, and it will give you all your security groups for that account and region. That's great, but there's a number of cons to this approach as well. When you have very large AWS infrastructures, they tend to get very slow at polling. This is a problem that we have at Netflix. We have so many resources that it just takes too long to get a list of all of them. Another big problem that we have is for certain APIs like describe instances, we actually won't get a response back. It'll actually time out because we have so many instances. So we have to be careful with how we frame these describe calls where we have to provide special filters in so we could get responses back in a timely manner. One problem, too, is that you might not see what new changes happened since you last issued a describe call. So if your infrastructure is changing frequently, you'll have to issue many describe calls very aggressively in order to reduce the latency between when you saw something and when you saw it again. This, of course, is a big problem with rate limiting. Who here has problems with rate limiting? A couple of people raised their hands. This is a big problem at Netflix. The more stuff you have, the more API calls you need to issue. The more API calls you issue, the more likely you are to be rate limited. Like I said earlier, this is the are we there yet approach to inventory collection. If you constantly ask someone, are we there yet, are we there yet, are we there yet, they're going to get bothered with you and tell you to stop. And AWS does this in the form of a rate limit. Because you're not AWS's only customer. They have lots of customers, and they have to make sure that their services are up and running for every single customer. And if you get rate limited, that's really going to slow you down, because now you can't issue any more API calls until that rate limit expires. Another issue is that you don't get the CloudTrail context. You want to know, given these resources, who made them, how were they modified, when, and how. CloudTrail is stored somewhere else. So you need to do this non-trivial process of mapping your CloudTrail data with your inventory in order to figure out that information, which is very hard to do. My clicker's not working. There we go. Event-driven approaches. So the pros to an event-driven approach is that they're fast. You can react to changes as they happen immediately. This allows you to get a timely state of your infrastructure and also allows you to react to changes as they occur. So if you see something in your infrastructure that is insecure, you can very quickly react to that and fix it. And this can also reduce rate limiting because you're only responding to the actual legitimate changes in your infrastructure. There's cons to this approach as well. They tend to be very complex. There are lots of components that make this work, as you'll see later. There's also a big problem with event lossiness. Amazon does a great job at delivering events to you, but it's a distributed system, and distributed systems have failures. You have to be tolerant of those failures. And in order to account for any missed event you might get, you're still going to have to poll anyway. So even in an event infrastructure, you'll still have to have a polling component. But the benefit is you don't have to poll nearly as aggressively. You can poll every couple of hours and still be OK. Who here uses SecurityMonkey? Bunch of hands went up on that one. SecurityMonkey is an open source tool that we developed in 2014. It is a polling-based infrastructure. It is based on Python, and it was originally developed by Patrick Kelly, who's a very talented engineer on my team. The way SecurityMonkey works is that there's three main components. There's a watcher component that goes out and describes all your infrastructure. It describes your S3 buckets, your SNS topics, your SQSQs, et cetera. It gets all of those configuration details. It stores it to the database with change history over time. There are then auditors that look at those configuration details and try to find insecure configurations. There are then reporters that then take all of those details and send emails. They can send JIRAs. You can expand that to add other systems as well. Here's a screenshot of SecurityMonkey. SecurityMonkey intends to be a single pane of glass that you can see all of your infrastructure resources. On the left-hand side, you'll see a search component. Over here, you can drill down based on the region, the resource type, the account, the name of the resource, as well as search inside resources that have certain criteria. Let's drill into one of them. So here's an S3 bucket. On the bottom, you'll see the configuration for this bucket. And there's one thing to note. This S3 bucket has an ACL that grants the all users group read access to this bucket. So this is a public S3 bucket. SecurityMonkey's auditors saw this and created an issue saying that this is an internet accessible bucket. This is very important because it allows you as a security engineer to find and work on the resources that need your priority the most. So let's discuss some challenges that we have faced and that you may also face if building out one of these systems. We developed SecurityMonkey in 2014. And back then, our infrastructure was totally different. Back then, we only had a small handful of AWS accounts. We had a small handful of roles that every application shared. Same with security groups. We weren't even in VPC yet. Today, that's a very different story. We have over 100 accounts now. We have thousands of IAM roles across all these accounts because we now have an IAM role per application. The same with security groups, and now we're in VPC. So we have thousands of security groups. We also grew in our S3 usage, and our SNS usage, our SQS usage. Every imaginable resource in AWS has massively grown since then. And at that time, and up until very recently, SecurityMonkey only ran on exactly one instance to handle the API, the UI, the scheduler, the watcher. Everything ran on one instance. And when we first developed SecurityMonkey, this was OK. For a while, this was fine. One instance was perfectly capable of handling this. But that's not the case anymore. Our infrastructure grew so big that earlier this year, SecurityMonkey stopped working hard. We saw extremely stale data on the order of weeks old. In many cases, we didn't see anything at all. This is a big problem for us. Our team, we're constantly in SecurityMonkey. It's one of our most critical tools. There's not a day that goes by where I'm not in SecurityMonkey searching for an S3 bucket or looking at an IAM role. And we also provide assistance to users where if they're having an access denied issue, we have to see, OK, does the role permit it? Does the bucket permit it? Does the topic permit it, et cetera? So this was a big problem for us. It prevented us from doing our job effectively. So earlier this year, I spent a lot of time looking at how to make SecurityMonkey more scalable for our infrastructure. So I pulled out all the old scheduling logic. I replaced it with a Python library called Celery that does task orchestration management in Python. And that worked really well. We made a 1.0 release in January, and now I'm happy to say that SecurityMonkey now runs, instead of one instance, it runs on over 40 instances today. So this is what it looks like now. We have a user interface component fronted by a load balancer, and many UI instances behind it. The way Celery operates is that there's one component that acts as a scheduling node. It tasks a set of workers to go out, and for every account, for every resource type, it describes all the resources, it runs the auditors, reporters, everything. In the back end, we have a PostgreSQL database to store everything, and we actually make use of Postgres Aurora at Netflix, and that works really well for us. There's also an Elasticache Redis cluster that is used by the Celery library to task the workers and the scheduler. What we actually did is, in order to get more priority, we made a separate stack of workers and schedulers for different resource types. For instance, we have a dedicated stack for IAM, one for security groups, for S3, for SNS and SQS. And that allows those workers to get just those resource types so we can operate it much faster and get that data with priority. So all is well, right? Well, unfortunately, it's not. At our scale, it's still too slow. Our environment is just so big. It takes us more than 30 minutes to pull for IAM roles and security groups and SNS topics in just one account. That's how many we have. And a big problem for why that happens is because we get rate limited. As we're describing all these resources, we hit a rate limit. And the way you recover from that is you have to do this song and dance of, OK, you get rate limited, so you have to back off a couple of seconds. And then you try again. And if you get rate limited again, you have to back off a couple of seconds. And you have to do this ad infinitum, ad nausea, until finally you get everything. So it takes 30 minutes plus to get everything in just one account. That's not quite the timeliness we want. You also don't get the CloudTrail context. We still don't know who created these changes, when and how. We want that to be with the configuration changes. So this is a limitation we have. But really, the biggest problem we have is just scalability. SecurityMonkey is a great tool. The changes I made to it earlier this year make it even better for more customers. But our infrastructure has outgrown it and continues to outgrow it. Really what this means is that polling is not effective at our scale. It's just not a good way of getting inventory with the size of environment we have. And we realized this back in 2016. We wanted to make an event-driven infrastructure for SecurityMonkey. And at that time, Amazon released this brand new feature that was exciting. It was called CloudWatch Events. And how CloudWatch Events works is if you have CloudTrail enabled in your account, CloudWatch Events will fire whenever a change is made. And it will tell you what was modified, and it will give you the full CloudTrail context about the change within seconds of it happening. This is great. And so we did this experiment. We codenamed it Banana Peel, where we took the most critical components of SecurityMonkey, and we stripped it down, and we made it into a Lambda function. And how this worked is whenever something would happen, the Lambda would be invoked, it would describe the asset, and save the details to the database. And this would take under 30 seconds from start to finish. This was really great, and we're really excited about this. But we had some limitations. The biggest problem we had was that we had to orchestrate how to set this up. We had to centralize all these events into one account. And we didn't have a good way of doing that. We instead made use of SNS. We forwarded everything to a central SQS queue and then had a Lambda run every 5 minutes to check that queue for any changes and then do its thing. But this had big problems because we were rapidly growing the size of our environment, and we were going to hit SQS policy size limits. This was a problem for us. The technology we really were missing was CloudWatch event buses. This allows you to centralize all those CloudWatch events into one spot. But this didn't come out until another year later. Another big thing is that as our information security team has grown tremendously over the years, we wanted to take the data that was in SecurityMonkey and make it far more available for other systems to address a number of other use cases. So we wanted to take SecurityMonkey and break it into smaller components so that we can make its data go much farther. And we learned a lot of lessons from Banana Peel. And that now feeds into a new tool that we're developing called Historical. Historical is a serverless, event-driven application that tracks changes to your AWS resources within seconds of a change, and it maintains the CloudTrail context of that change. What's really powerful about Historical is that it enables downstream consumers to respond to those changes and with full context so they can make intelligent decisions. We're developing Historical open source. It is available today on our Skunkworks repository. And the reason why it's a Skunkworks project is because it is in very active development. There is a lot of work we still need to do for it. We've made some really great changes to the infrastructure, and we're very happy with where it's moving. How Historical works is that it is an owl. It is perched over your environment, and it can see all your resources, sees all the changes, and notifies the downstream consumers of it. It is a flexible system. It is not a closed loop. This is very important. Today, Historical is currently monitoring EC2 security groups in S3 buckets. I'm actively working on a feature that I hope to get completed by the end of this year that will provide IAM capabilities, so we'll have support for roles, groups, users, managed policies, and server certificates. I also included a basic Terraform template that you can use to install Historical in your own environment. So let's discuss some general concepts. Like Banana Peel, a CloudWatch event will tell you when something happens in your environment. When that happens, we then go out and we describe that resource in question. We then check if that resource's state is actually different from what we previously knew about it. And if it is, we then save a new change record. We also notify the downstream consumers of that change. This is important. We don't want to create unnecessary noise for the downstream consumers. So if you have something in your environment that is constantly putting over the configuration of an item, that is a very common pattern that many tools do. It's to enforce that an item state is set. But if you're listening to CloudWatch events, that could be very noisy. We don't want to alert downstream subscribers of changes unless they really care about that. So we do some noise reduction, and we will only alert downstream subscribers if something actually changed from what we previously knew about it. We want to immediately process those CloudWatch events. It's very important that we do that, because when we get a CloudWatch event, it indicates that our environment is potentially different from what we previously knew about it. We also have a poller. The poller polls for all resources every couple of hours. It's basically it's your insurance policy in case an event ever gets lost. The lossiness is very low, but you still need to have a poller component anyway. It's every few hours, super low priority. We also put a full stack of historical in regions where we expect to receive the majority of our CloudWatch events to derive. So in the majority of all of our Netflix infrastructure, we have a historical stack there. We also create per resource type stacks. We have a stack of historical for S3, one for SNS. We'll have one for SNS, but one for security groups, one for IAM in the future. This is done for a number of reasons. Number one, it lets us address the nuances of each resource type, as well as we're creating lots of new features for historical, we don't want to break anything in that process. I have to make a note about SQS and Lambda. We absolutely love this feature, and you should too. It is great because it gives you massive concurrency on your Lambdas. If you use SQS to invoke your Lambdas, it will spin tons of Lambdas all at once. It's great. It auto-scales for you. It also allows you to retry on failure without blocking your entire pipeline. So you don't have to poison pill your function. It has the ability of doing dead letter queues, which we're not using today, but we will in the near future. And this last feature is really cool. Message delays. So why would that be cool for? So if you have lots of things going into your SQS queue to invoke your Lambdas, you're going to have all these Lambdas spin up at one time. And if these Lambdas are accessing a resource, you would have a thundering herd problem where all these Lambdas at one time are just hitting against this resource. That could be a big problem for you. So what message delays do is you could set a randomized time from 0 to 900 seconds to put this message onto the queue, and it won't invoke your Lambda function until that visibility occurs. This allows you to introduce jitter in your Lambda function invocations to avoid that thundering herd from happening. We make use of message delays in polling because it doesn't have to run frequently. It just needs to run at least once a day. It's a great feature. We make use of CloudWatch event buses. Every single account is configured to route their bus to one central account that we use for processing those events. We also have an IAM role that lives in the historical account, and the IAM role can assume into all of the destination accounts that needs to be inventoried. This allows historical to get all the inventory that it needs in that account. And here it is. This is what it looks like. I mentioned before, there's a lot of stuff that makes up a event-driven infrastructure. At a 1,000-foot view, historical has multiple regions. There's a poller that goes out and describes all your resources. It runs very infrequently. There's also a collector to go out and fetch the details of your resources. We save those details to a global DynamoDB table that has a cache of the existing resources that are in your environment. There's a Lambda function that does a diff between what we currently know about a resource and what we previously knew about a resource. That stores details to another Dynamo table that stores the full change history over time. And then we publish those details to an SNS topic that downstream consumers can subscribe to. Now, if I was in the audience, I would think it looks like a bunch of M&Ms on the screen. It doesn't make any sense. So let's disambiguate this. We have a primary region. And the purpose of the primary region is to process all of the in-region events that occur. It serves another purpose. We want a full global view of our infrastructure, but we don't want to deploy an entire stack of historical there. So what we do is we put very minimal pieces of infrastructure in the regions that we don't have a lot of infrastructure in, but still care about. So for those regions, we have a CloudWatch change event pointing to an SNS topic that routes all of those messages and events to the primary region for processing. So the primary region processes all the in-region events and all the off-region events. There's a secondary region, and it's just like the primary region, but its concern is just the in-region local events. This is done so that you can have fast reaction to the CloudWatch events that occur. The poller runs every few hours. It's composed of two different Lambda functions. a tasker lambda that basically iterates over all your accounts and regions, and it tasks a polar lambda to list all the resources in a given account. That will then task another lambda function called the collector to go out and describe the details of that resource. The collector is invoked one of two ways. Same function, just two different ways of being invoked. One is from the polar, and the other is directly from CloudWatch change events. I mentioned previously that we want to give CloudWatch change events top priority. That's because when something changes in our infrastructure, we immediately want to collect it. The reason why there's two invokers here is that if you just had one invocation mechanism, you would have your change events sandwiched in between polling events, and that would slow you down. That was a mistake we made. We learned our lesson. So we created two different ways of invoking, and that allows us to have priority to those CloudWatch change events that occur. We then save those details to a global DynamoDB table that we call the current items table, and that table acts as a cache of all the existing resources that we see. There's a DynamoDB stream event on this table that invokes a Lambda function that does some noise reduction. It then takes the details of that resource that just got changed, and it triggers a differ Lambda function, which actually looks at the previous known state of that resource and the current state and checks to see if there's actually a material difference between the two. If there is, then the differ saves a new change record to the durable items table, which is a global DynamoDB table with all of your changes over time, with the CloudTrail context. And this is where the magic happens. At this point, there's a DynamoDB stream on the durable table that invokes another Lambda function that takes all of the details of that resource, the full resource config, along with the CloudTrail context, and it sends that onto SNS for any downstream consumer to care about that change. And they get the full context of that change with the CloudTrail context, and they can then make very intelligent choices with that. This is great. So, high-level overview. Multiple regions. We want to have a full global view of our infrastructure. A poller that runs every few hours. Nothing crazy about that. It's not aggressively polling. Just every few hours it has to run. There's a collector that goes out and describes the resource in question, especially after a change event occurs. We give priority to that. There's then a DynamoDB table where we store a cache of the existing resources in our environment. That eventually invokes a Lambda function we call the differ to diff the change of the current resource we know about as well as the previous state. And if it's different, we save a new change to the durable items table, which invokes a Lambda function that serializes that event in the full context of which and publishes that change to downstream consumers so that they can make proper use of that. So how are we using this internally? Historical is still new. We're still adding new capabilities to it. But there's two very awesome use cases we have right now. Number one, we use historical as a source of truth for enabling S3 server access logs everywhere in our infrastructure. We have automation that relies on historical to see when S3 buckets are created and if they have the right configuration set so that we can ingest all the S3 server access logs to address a number of very important use cases internally. So we have every S3 bucket at Netflix with S3 server access logs enabled automatically because of this. This is important. This next one we're really excited about. StreamAlert is an open source tool developed by Airbnb that allows you to ingest a lot of event data and have real-time processing against it. We previously made use, we're currently making use of StreamAlert with CloudTrail. So we can do some really interesting alerting upon that. We previously had an alert with CloudTrail being ingested into StreamAlert where if a security group had wide open security group ingress, we would create an alert for that. CloudTrail dumps its logs to S3 every 15 minutes. That's a pretty long time in order to respond to an active potential problem in your infrastructure. We replaced that with historical for this particular alert, and we dropped the time down. Instead of 15 minutes, we brought it down to 1 minute. Anywhere in our infrastructure, any environment, any account, any region, if you create a wide open security group rule, we'll be alerted within 1 minute from creation of the rule to completion of the event. We even made a Slack integration for it. We're really excited about this capability, and we really look forward to add more stuff to this in the future. So what are our goals? We want to add a lot more AWS resource types. We also need to make some enhancements to make it easier for us to do that. Right now, in our rapid innovation mode, we have a lot of duplicated code. In the coming months, we're going to clean that up, so it's much easier to add new technologies to historical. We're going to massively increase the speed. There's current areas where there's some slight bottlenecks. We're going to improve that, so it's even faster. We want to make some documentation improvements. I spent a lot of time on that. Please let me know if the docs are not correct, and I will make effort to fix that. We also want to, at some point, put a UI and API in front of it as well. So what about SecurityMonkey? SecurityMonkey is a great tool. It took us very far. I use it every single day. But SecurityMonkey cannot scale to the size of our infrastructure. Our infrastructure is just too big. So we need to focus on tools like historical that can operate at the scale that we need to operate. As a result, we're going to start supporting minor bug fixes only. However, community contributions are always welcome. Please submit them, and I will merge those in for you. If you're interested in taking ownership of SecurityMonkey, please come talk to me after this talk. Before we leave today, I want to talk about what our desired AWS infrastructure state is. We want to have a fast-responding, auto-correcting infrastructure. What that means is that we want to discover bad signals and fix them automatically. We want to prevent and undo large automation scale failures. So what does that mean? With our infrastructure, we are heavily dependent on automation. And I don't know about you, but I've made bugs in automation, and they can cause problems remarkably fast and remarkably with tons of impact. And that's bad, and that's stressful to fix. We don't want our customers to not be able to stream Netflix because of a bug in automation. So what we want to do is create an infrastructure where we have the full state of everything. We know exactly what changes, who changed it, and at any time, we can write tooling to very easily revert gigantic amounts of changes in our infrastructure to a known good state. This is where we see ourselves moving in the future. We want to make our infrastructure incredibly robust. We hope that this is a similar use case that you have as well, and we hope that historical can get you there in the future. That concludes my talk. If anyone has any questions, I will be at the Netflix booth, and I'm also giving away these awesome historical stickers, so please come by and get yourself one. Thank you.